All right, today we're looking at the alternating series test. Now, the alternating series test actually has three outcomes. The first is absolute convergence. Absolute convergence means that if you get rid of the part that makes it alternating and it converges, then it converges absolutely. Completely converges. The second is conditionally converges. That's where we'll use the alternating series test. Then the third is diverges. Now, we first need to talk about what it means to alternate. An alternating series is a series like we've normally seen, but the terms alternate from positive to negative and back and forth. Okay? It usually has something that we call the alternating part. So in this case, the -1 to the n plus 1 is what's making it alternating. So let's talk about what these different things mean. Absolute convergence means, hey, this series would have converged even if it wasn't alternating. Because alternating can only ever make a series converge. It can never make it diverge. So it would have converged even if it wasn't alternating. Now, sometimes the series, like this series with the a sub n, that diverges. But by throwing in an alternating part, by making the terms alternating, then it suddenly converges. This is conditional convergence. This means it converges specifically because it is alternating. Otherwise, it would not converge. And then diverges means it doesn't converge at all. So the alternating series test is only used to check for conditional convergence. And it says if the limit is equal to 0 and the terms are decreasing in magnitude, so the current term is bigger than the next term, then it's going to be conditionally convergent. Let's look at our first example. So we have it's a sum from n to infinity, n equals 1 to infinity of -1 to the n plus 1 over n squared. All right, this is a series that is alternating. Let's start by getting rid of the alternating part and checking for absolute convergence. So we're going to check to see, does this converge? If it does, then hey, the alternating part doesn't matter, it absolutely converges. So p is equal to 2, which is bigger than 1. So we would say it absolutely converges by p series. Don't even need to check the alternating part. We know that because it converges when it's not alternating, it'll definitely converge when it is alternating. Let's check this next one. All right, we'll start by getting rid of the alternating part. And we'll check this. Well, this one, if we do p series, it diverges. That tells us nothing about the alternating series. So we'll go to the alternating series now, and we'll check our two conditions. We'll say first, is the limit of the sequence without the alternating part, so 1 over n, equal to 0? Is that equal to 0? Well, yeah, as n goes to infinity, that's 1 over infinity, which equals 0. All right? The second is each term in the sequence smaller than the current. So current term bigger than or equal to the next term. Well, it just means plugging n plus 1 into the sequence. Well, let's check. We'll cross multiply. N plus 1 is greater than or equal to n. Subtract the n's. 1 is greater than or equal to 0. Hey, look, that is a true statement. Since both of these are true, we can say the series converges conditionally by the alternating series test. Okay, converges conditionally by alternating series test. Last case is one that doesn't converge at all. So we have the sum from n equals 1 to infinity of 2n over 3n plus 5. That one diverges by the nth term. Now, this is one of the best cases to end up with, because if it diverges by nth term, you've already checked the first step for the alternating series test. Remember, first step for alternating series test is check, does the sequence itself equal 0? Well, this is just the nth term test. Nth term test says if it's not equal to 0, it diverges. Well, since it diverged by nth term, this equals to 2/3, which is not 0, which means we don't even need to check the second test. We know that this is going to diverge. Now, there are some options. You can say diverges by nth term test or diverges by alternating series test. Either one is fine. I'm going to just say diverges by nth term test. Okay. Last thing we're going to look at is the alternating series error bound. There's a lot of text, so you can stop the video, take a picture, whatever you need. But let's talk. It says if we have a conditionally convergent series, so it's alternate, decreasing in magnitude, limit of 0, then it has a sum. We know that. Okay, there's some sum out there. Now let's say we take the nth partial sum, so the sum of the first 4 terms, first 5 terms, some number of terms, and sum them up. That's going to be an approximation. That's not going to be the exact sum. But the error in that approximation, how far we are off, that's what this means right here. That's the error. The error will be less than the absolute value of the first omitted or truncated term. So that's the error is going to be less than the next term in the series. So let's look at an example. We're going to start by summing up these first 4 terms. So we'll plug in the first 1, 2, 3, 4, get 1 over 1. So 1 minus 1/2 plus 1/6 minus 1 over 24. And normally, these would be a calculator problem. So we plug it into the calculator. And we get 5 over 8, which is 0.625. Then we want to use the alternating series error bound to show that this approximation differs from the actual value by less than 1 over 100. This is where that error bound comes in. It seems like a really complex thing, but all it's saying is the error, which is the same as saying the absolute value of S minus S4. This means the sum, and this means our approximation. And so that should make sense. Sum minus approximation is the error in our approximation. This error is going to be less than or equal to the next truncated term. Well, what's the next term we're missing here? The next term would be 1 over 120. Well, that is all fine and good, but does that answer the question? Well, the question just says, show that it differs from the actual value by less than 1 over 100, or show that the approximation is less than 1 over 100. Well, our approximation is within 1/120th. That's less than 1 over 100. We answered the question. We're done. Lastly, we want to use our results to explain why S cannot equal 0.7. Well, because we know an error, a bound of error, we can create an interval for which S lies in. So S is the sum. S has to be between our approximation, 0.625, plus the error, 1 over 120, and our approximation, 0.625, minus the error, 1 over 120. Our sum has to be somewhere between there. So if we actually add those up, we get 0.617 as the lower bounds and 0.633 as the upper bound. So our sum has to be somewhere between those values. So why can S not equal 0.7? Because 0.7 does not fall between these two values. 0.7 is not in between. So that's our explanation. All right, that's it for alternating series. Let me know if you have any questions. Y'all have a great day.